Hi, class. So I'm going to record a lecture here on centripetal acceleration and force. So this is section 6.2 and 6.3 in your book. And yeah, circular motion, centripetal acceleration, and force, these are not easy concepts necessarily, and it really helps to write these out. So I'll go ahead and do that. Okay, hopefully that's clear enough to see. And we're going to have, this is going to be circular motion again. So want to have a good circle there. That's probably good enough. Okay, then we're going to have basically the same as before. We're going to have a theta, some displacement. It's going to be moving around with a constant angular velocity. And so this is again going to be, we're going to have R. I'll do that in another color. This is going to be S here, S. And then as it's going around, we have velocity vectors. So maybe I'll just move my S a little bit up there so it's a little easier to see. Because I'm going to have to draw this velocity vector here. So we have, well, that's got to be perpendicular to where we're going. So that's going to be V. I'll call that V1. And then that's V2. Okay, so the way this works, and it breaks it down in your book, but as you can see, so each one of those vectors are going to be the same length, but you can see that as it's going around a circle, the direction is changing. So we know by vectors, direct magnitude and direction both matter. So actually what that does is it creates this centripetal acceleration force. Anyone who's swung a mass on a string or anything like that, or has taken a tight curve, knows that this force is real. So the way that works is basically some vector manipulation. So we see, draw these two velocity vectors, and we'll just kind of move them out here and put them end to end. And so let's call that one 1 and that one 2, or 1 and 2. Yep, so that's pretty much it. And then there'll be the difference is that there. So that is delta V from the vectors. So delta V is V2 minus 1. And it's just direction. I won't write all this out necessarily. So since the magnitude of 1 and 2 equal each other, basically this is going to this effect will increase, centripetal acceleration will increase as the radius increases. So you can imagine, I always think of the hammer throw, like in the Olympics. And you know that if you have a little bit of string and you're swinging around, and then the string gets longer, the force will get more. The longer the string gets, the more force and acceleration you'll have. So it's going to be, and so as the radius increases, this will increase, and so will S. So I can kind of, let's see what we got. Yeah, we'll just do it that way. And so that will be R. So the difference in it over the magnitude is going to equal the change in the arc, or S, distance around there, over R, that magnitude. And so that's a property of similar triangles. I won't go too deep into that. Really what we're trying to get it to is the equation here, which is going to be the most important part, and you'll just is the equation. So we have our change in velocity and velocity. So we just manipulate this a little bit, and I'll just bring it over here, I guess. So delta V is going to equal V times delta S over R. And then all we need to do is basically divide by delta T. So delta V over delta T, and that'll give us our acceleration. It's going to be V over R times delta S delta T. And so we know from before that this here is basically the velocity, and we already have the velocity. And this here is going to be the acceleration. So then we'll just write it as centripetal acceleration is equal to delta V over delta T, and that is equal to V over R times B, which is equal to B squared over R. Okay, so it's kind of a quick way to do this, but really this equation is what you're really going to need over and over again. Yes. So when you're looking at centripetal acceleration, it's going to be V squared over R. And again, that's going to be the points, if you're on the outside here on a circle, moving between those points is velocity. So the point on a wheel or something like that. So then from there, we just do the force. So force is just a mass times acceleration. So I'm going to erase this and do the force. I can erase all this. And then we'll just do the force here. So here we just have AC equals V squared over R. And the force, we'll do that centripetal force is equal to the mass times AC. And that's just a mass times velocity squared over R. And we also know from omega, it's going to be mass omega squared times R. And so yeah, we can think of that as we have the mass at the end of the string, a radius R. So we'll say that's a mass, and it's going around, and we'll draw the centripetal acceleration force. So the acceleration is going towards the center each time, like that, like that. So that's AC, and that's also the force. So the force is always going to be towards the center. And you can think about that. So the radius here is like your string. So and it's pulling out that way. So let's see use purple there. So anyway, so that's going to be the force pulling out, and then so the centripetal is opposite. So yeah, really that's all you're going to need to know. So you're all this here is all you really need to know for the centripetal force. And then it all comes from this V squared over R equation. So once you have a centripetal acceleration, all you need to do is multiply times velocity, and you'll have the force. So yep, that's centripetal acceleration and force. And there's lots of different problems you can have with this. A lot of them are cars going around a curve. Then they have a certain amount of friction. So I can draw that out real quick. So yeah, we'll say a lot of times it might be ice or something here. It'll be going around a curve or some block. And you'll have to think about this. I won't draw it in 3D. But basically, say it's spinning, you'll have, that'll be your centripetal force. and then you'll have some force going this way. That's friction. And so for it not to slip, the friction has to be equal to centripetal force. So then you also have gravity and a normal force here, the weight. So as we saw, this friction is going to be mu times n, centripetal force, that's going to be mv squared over r. We're going to say the r is going to be the circular radius, and then w is mg. The weight, normal force is going to equal the same, so that's mg. And yep, that's how you would solve a simple problem like that. Okay, I hope this helps clear things up. I know centripetal acceleration force is not always that easy, so please ask me if you have any questions. Thanks.